Hello class, welcome to science. Today we are going to be talking about the science behind sound. With you, you should have your Slinky flipbook, which you will be filling out today, and this needs to be completed when you come to class. As I said, today we are going to be talking about the science behind sound, and we are going to be using a Slinky to demonstrate a sound wave. So, what exactly is sound? Sound is a type of energy made by vibrations when any object vibrates. It causes movement in the air particles, and these particles bump into other particles close to them, and those particles bump into other air particles close to them and makes them vibrate. This movement is called sound waves, which our Slinky represents right here. And these keep going until it runs out of energy. If your ear is within range of these sounds, you hear the vibration and you hear the sound, and that's the sound wave. So think of the ocean. When waves roll into the shore, the waves keep going until they run onto the shore and flatten out and the energy is gone. That's kind of how a sound wave works. The sound wave keeps going until the energy is all gone. If you look at this Slinky right here, the air particles are going to move, and this is going to create the motion of the Slinky. I just gave you a brief definition of sound, so now I want you to take your flipbook and stop this video and write in your own words your own definition of sound. There are 6 terms that I want you guys to know when you are finished watching this video: vibration, compression, wavelength, frequency, amplitude, and pitch. All of these terms have to do with sound waves. We already talked a little bit about vibration in our definition of sound, and so we're going to start off by defining what vibration is. Vibration is the constant movement to and fro, and sound is actually a vibration. So think about this. When a player or an instrumentalist blows through their horn, the air inside the horn vibrates, and the vibration of that air is what makes the sound. The second definition we're going to talk about is compression. And compression is regions of air molecules that are squeezed together or spread apart. So when you have an object and it vibrates, the movement of the vibration goes back and forth. When the movement goes forward, more air particles are pushed forward, and when the movement releases on the other side, less air molecules are pushed forward. Again, think of the ocean. So when a wave is coming in onto the beach, it is pushing more water, but when it's pulling back out, it's not pushing as much water. That's how sound waves work. So as sound waves travel, some molecules are pushed together, and that is called compression. And then when they are more spread out or not pushed as much, it's called rarefaction. So let me show you on the Slinky what that looks like. If you look right here at the Slinky, I'm going to show you what a compression looks like. So when air molecules are pressed together as in a compression, the air molecules are going to be closer, like this, or like this. And in between here, the air molecules are looser, and that means that that's a rarefaction. Now that you understand the concepts of compression and rarefaction a little bit more, I want you to stop this video, turn to the second page in your Slinky booklet, and I want you to label the compressions and rarefactions of each part of this sound wave. The third term that I want you to know about a sound wave is wavelengths. And wavelengths is the distance between 2 compressions or 2 rarefactions. Now, the catch is that wavelengths can be different lengths. So let's take a look at what this might look like on the Slinky. So right here we have a compression, and right here we have another compression, and in the middle is a rarefaction. So the wavelength would go from this compression right here all the way to this compression right here. Or if we're talking about rarefactions, it's going to go from this rarefaction right here to this rarefaction right here. Now it's time to add the wavelengths to your sound wave in your Slinky booklet. So flip to that second page, and this time I want you to draw lines from the compressions to the compressions and the rarefactions to the rarefactions showing the wavelengths. So go ahead and stop this video and do that now. The fourth term I want you to know is frequency waves. And frequency waves is how fast or slow sound occurs. When the vibrations of sound are slow, that produces a low frequency wave, which means the sound is low. And when the vibrations of the sound waves are fast, that means the sound is high and it produces a high frequency wave. So there are some characteristics about high and low frequency waves that I need you to know. Use the third page with the chart about frequency facts to fill in the chart with these terms. A high frequency wave is thin, small, short, and tight, and it produces a high sound. Low frequency waves are thick, big, tall, and loose, and they produce a low sound. Think about the strings on a guitar. The lowest and thinnest string produces the highest sound because it is thin, just like the high frequency wave. And the thickest string on the guitar at the top produces a lower sound because low frequency waves are thick. Now I want to show you what a high and low frequency sound wave looks like. Because the vibrations are moving faster, a high frequency wave is going to look like this. And because vibrations are moving slower, a low frequency wave is going to look like this. So using the string that was provided to you with your Slinky booklet, I want you to show me what a high and low frequency wave looks like. The fifth term I want you to know is called amplitude. And amplitude is also about vibrations. And amplitude means the loudness of sound. So if my finger is standing still right now and my other finger is vibrating, amplitude is the distance that my finger moves back and forth in relation to the one that it's at rest. In amplitude, when a loud sound is made, many air molecules have been vibrated with a lot of force. But when a soft sound is made, there are fewer molecules being vibrated and with less force. To see what it looks like on our sound wave Slinky, the peak of each compression or rarefaction is where amplitude takes place. Open up your flipbook and complete the page on amplitude. I want you to compare and contrast amplitude and compression because there are some similarities between the two, but also some differences. The last and final term we're going to talk about is pitch. And we've actually already talked about it a little bit when we talked about high and low frequency waves because pitch is the high or lowness of a sound. And it also refers to how accurate a sound is. So on the last page of your flipbook, I want you to give your best guess and I want you to write what you think pitch really is. When you come to class today, we are going to explore what that is and we're going to use some manipulatives to listen to pitch and relate it to other objects.